We're continuing our discussion on history of the second law and kind of the foundation of the second law. How do we reach the conclusion of the second law of thermodynamics? And so in this point, we're in chapter 6 of the Changle and Bowles text, and we're talking about some of the different terminology that gets used when we talk about devices that helped us formulate what the second law is. I mentioned earlier, I normally don't use the term thermal energy reservoir or any derivation of it. I'm normally going to use the term source and sink um, because this basically specifies the direction which energy is going. So a source is um, any kind of reservoir that's going to supply heat to our system, and a sink is any reservoir that's going to absorb heat. I'm going to go find real quick some images. All right, so the term heat sink, you've probably heard of before. A heat sink is just simply this device. It's basically a hunk of aluminum, really. When we use the term heat sink, that's often what we're talking about. Sometimes it can be made out of other things. These look like they're probably copper. But a lot of times it's this hunk of aluminum with these fins on it. And then we use a fan to blow air through those fins. And so what's happening is on the underside of these heat sinks, um, you can kind of see these are going to be mounted on circuit boards. And what's underneath this hunk of metal with these fins on it are going to be a little chip, a little computer chip or processor chip or something like that, where this electronic device that has lots of electricity coming in, some electricity going out, and a lot of the electricity that's going in actually gets converted to heat inside that electronic device. And it's a very small amount of mass. So I've got a lot of energy coming in, generating a lot of internal energy inside, and it's a very small amount of mass. So already done some of the calculations. You know what that means to the change in temperature. It goes up very quickly. Well, these electronic devices, if they get too hot, they don't work. You let the magic blue smoke out, so to speak. So what do? We have to keep these things cool. So a heat sink is a piece of metal that is very carefully shaped in such a way that when we blow air through these fins using a fan, that those fins are very good. They're a pretty good shape at conducting heat away from these sensitive electronics. Now, an interesting bit, I don't want to spend too long on this, but um, we're actually finding that this is a technology that we can actually improve on using additive manufacturing. So metal 3D printing, for example. Here's some examples of different shapes of heat sinks that we can produce today that are much more complex and much more effective because of the shape, because of the surface area. These intricate shapes are much better at moving heat away than, say, something like this set of aluminum fins here. This is very easy to machine out with simple tools, but because we have equipment now that can produce more complex shapes, we now have the opportunity to really go in, and a lot of research is being done right now in this area of generating heat sinks that are more efficient and more effective because we have technology that we didn't have even 10, 20 years ago. So all that to say, again, hopefully that gives you a little nugget of holding on to what is a sink, what is a heat sink. Well, it's just some body, some object that is there to absorb heat away from our system, and a source is some reservoir, some object that is providing energy to our system. Okay. All right, that's again, kind of the basics. A lot of what we're doing in chapter 6, there are some problems we're going to have to solve. There are some numbers we're going to put to things. But a lot of it really is, there's a lot of concepts that we're needing to get in place before we get into the second law. One of those is the idea of an engine and what an engine does for us. Um, some of you guys have had intro to engineering with me, and we've talked about the difference between engines and motors. We don't necessarily have to focus on that here, but we do want to talk about what an engine is. An engine and what this does for us is I've got this statement here. You can see it is easy to convert energy and work into heat. but it is pretty difficult to go the opposite direction. So if I take my hands together and I rub them together right now, you can hear some sound being generated, but I'm actually generating a good amount of heat with friction between my hands there. I'm taking work where I've got motion, energy of motion, and I'm turning some of that into heat. That's very easy to do. Um, Going the other direction, taking that heat and converting it into work, not as easy. And the other example I like to give here is um, I'm recording these in the summer, and maybe my wife and I want to go out and camp. And in the wintertime, I've got like a little space heater laying around, and got a room maybe that's a little far away from the thermostat and gets a little cold. And so I go to a big box store and I buy a little space heater, right? And I can push electricity through that space heater, and that's real easy. Electricity is work. Electricity is the moving of electrons. That's energy transmitted through the moving of electrons. So that's work. That's very consistent energy transmission. And it's really easy to turn that work, that electrical work, into heat, right? That's real easy. I just plug it in the wall and push a button. Basically, as long as electricity flowing through a circuit, it's generating heat. What if, as I mentioned earlier, it's summertime, my wife and I, maybe we go out camping somewhere, and I'm like, how am I going to charge my cell phone? I'm out in the middle of nowhere. I don't have electricity. I'm going to charge that cell phone up. Um, and I thought, hey, I got that space heater. It's not doing anything. How about I take that along and I take it out? I build a nice big campfire. I set that space heater next to the fire, get the fire good and hot, and I take my pocket knife and I cut the plug off of that space heater, and I wire that up to my cell phone charger, and I plug my cell phone in. I mean, hey, I can put electricity in, I get heat out, right? Can I just put heat in and get electricity out? Doesn't that make sense? And I asked this in class, and I'm always chuckled and amused by the faces I get. And normally everybody's nice and they don't call me an idiot, but no, that's not going to work. That's not how this works. Um, and really, kind of the second law is dictating why that doesn't work in a number of different ways. But we know that if I take, an electrical resistance, that's basically what this symbol here is. I'm saying if I take an electrical resistor and I apply a bunch of heat to it, if I take that electric space heater and I set it next to a hot fire, I'm not going to expect to get electricity coming out. I is going to be zero. The current flowing through this electrical circuit is going to be zero. I mean, it might not be completely zero, but it's not enough to do anything useful with. All that to say, it's easy to turn work into heat. It's much harder to turn heat back into work. However, we do have devices that do just that. We have devices that take heat and convert some of that heat into useful work. We call these devices engines, or specifically heat engines. That is what an engine actually is. A motor is a device that's going to convert some sort of mechanical work to another type of mechanical work. But an engine is a device that's going to take heat and convert some heat into work, into mechanical energy. That's the technical difference between those two devices. We're going to focus here on a heat engine. A heat engine is a device that's going to take some amount of heat, and it's going to turn some of that heat into work. What have I got here? Okay, so I do have an engine. So let's talk about some of the terminology here. Before I drew it out, I wanted to make sure that I've got an actual engine, and I'll draw it with you on my slides here. I was trying to remember how my slides were set up. So, how does an engine work? An engine is going to receive some amount of heat from a high temperature source, right? This guy up here, some amount of heat from a high temperature source. Going to pour a lot of heat in. Notice big band up here coming in, right? A whole bunch of heat coming in. It's going to take some of that heat and kick it out as work. And what can't go out as work, then it's got to reject the remaining heat to a low temperature sink. Remember, one of the statements was we can't only receive heat from one body and generate work and operate in a cycle. It doesn't work that way. I think that's the Kelvin Planck statement. we're going to have to do something else. So normally the something else is we have to reject the remaining heat that could not be turned into work to get it out of the system, out of the engine. That way the engine doesn't blow up, and then we can continue the cycle and get it back to its initial state. Right? A term here, terminology, working fluid. The working fluid is the fluid that moves the energy from one part of the engine to another or throughout the engine cycle, depending on how the engine is built and construction, what type of engine it is. So a steam engine is going to look a little different than, say, an internal combustion engine, although they're kind of doing the same thing. They're both taking heat and turning some of that heat into work and then dumping whatever heat they can't use and then repeating the cycle. Uh, of a There are two main working fluids we'll use, or that we'll consider in this course, especially two of them being water is one of them. Water has a very high specific heat content. It's fairly easy to obtain, fairly non-corrosive, but the biggest thing is it will take a whole bunch of energy before it increases in temperature. And that takes a whole bunch of energy to get it to vaporize. It's a really good way of storing a lot of energy in a way that's pretty safe to work with. And again, it's not toxic. It's just easy to move around and it's reasonably easy to acquire. Air is not bad as a media for a working fluid, and some devices are going to use air as their working fluid. But the water will has a much higher specific heat content than the air does. So that's the advantage of using water. But that's what a working fluid is. Whatever the media is for moving energy from one to the other. Now, here's where I'm going to draw this with you. So I'm going to switch to my document camera here. And I think I'm going to try to expand this out. So you can see the image here, but I'm going to go ahead and draw it with you guys. How am I for time? Not bad. I'm just going to go until I'm done and we'll start the next video from there. All right, so a heat engine. So I'm going to draw it. I encourage you to draw it in your notes. So I'm going to draw it with you. What does a heat engine look like? A heat engine is going to have some high temperature source, T sub H, high temperature source. That high temperature source is going to pour heat into our engine. That heat is going to go into a heat exchanger that we call a boiler. Right? So I'm drawing what's on the big diagram here, okay? But I'm going to draw it with you so you can draw it in your notes. So that boiler then is going to feed high pressure, high temperature working fluid, often that's steam, into a turbine. So this is kind of the modern version of a steam engine. That turbine then is going to extract, just like we talked about in chapter 5, work out of the system, out of the engine. Now, coming out of the turbine, I'm going to have a lower pressure, lower temperature steam, probably a very high quality mixture. We might simply get it down to saturated vapor, but we might go ahead and get it down to like 95% vapor, 5% liquid, a very high quality mixture. And I'm going to run that out of the turbine into another heat exchanger we call a condenser. The job of the condenser is to remove the remaining heat, and it's going to reject that to some low temperature sink, T sub L. So a body of water, the atmosphere, something that is at a lower temperature that can take it. TH is going to be some high temperature source like a coal fire, a natural gas fire, the sun, a nuclear reaction, something that is a very high temperature, can pour a lot of heat into the boiler, use that to generate a lot of high pressure steam, high temperature steam, run that through the turbine, extract work out. And then again, what heat couldn't be converted into work out needs to get rejected to get the system kind of back to basically so it doesn't blow up, but get it back to a point where it can operate in the cycle. Now, I've got low pressure coming out of the turbine. I need high pressure going back in the turbine. There's nothing in the boiler that's going to increase the pressure. I need high pressure here. And in fact, the pressure is just simply going to drop across a real boiler. We're going to assume boilers are ideal and they're not going to lose pressure. That's a fluid mechanics problem to look at the pressure drop from end to end. But all that to say, I need high pressure here. There's nothing from here to here across the boiler that's going to increase the pressure. So what I need to do is I need a pump. I need some sort of device that if I put a little bit of work in, that I can get high pressure. I need high pressure liquid going into the boiler, and it's going to boil it all off, and I get high pressure steam coming out of the boiler. So I need high pressure going into the boiler. And how do I do that? Well, if I get it all the way down to the liquid phase coming out of the condenser, right, if I get it all the way down to the liquid phase, I can put just a tiny bit of work in. Liquid doesn't squeeze, so if I apply work to it, basically what's going to happen is it's going to that I'm going to try to squeeze the liquid and it's going to squeeze right back. I'm going to jack the pressure up really quick without a lot of work. So I get a high pressure going in the boiler. That means high pressure out of the boiler going into the turbine. The turbine runs just fine, and the cycle continues. All right. So this is a heat engine. And my timer's gone off, so to keep these videos reasonably length, I'm going to start us there on the next video.